Okay, thank you. So let me just start with where this all started with this was Smale's thesis in 1959. And I've got this page up because we can save me giving the definitions. An immersion is a regular map. So a map with Jacobian is of maximal rank of the manifolds of the first into the second, as Smale said, right? And a homotopy is called regular if at each stage it is regular in the first sense, and if the induced homotopy of the tangent bundle is continuous. So here's what it looks like. Yeah, right. So if you have a piece of surface, an immersion is allowed to it can self-intersect. Okay, that's not a problem because rank is a local property, but you're not allowed to have cusps or folds like that where the rank would fall. And here's examples of a regular homotopy. It's a homotopy through immersions. So you start out and you follow the deformation parameter along here. Here's a good one, and at the bottom there's a bad one. You start and there's a point here. There's right. You get these are circles in the plane, but the deformations are completely analogous. Right, so you have 2 points of rank 0, so this is not a regular homotopy. Now, Smale already mentioned in 1959 that it's not trivial to see that a reflection of the unit sphere in E3 is regularly homotopic to the identity on the unit sphere. So that regular homotopy is what's called
inclusion.
Huh?
Regularly homotopic to inclusion.
Yes.
Yeah. You have to move in space.
Any two are regularly.
Well, Smale isn't here to defend himself. I think this is okay. So the idea is, it's not trivial to see that you can start out with a regular embedding, the usual standard embedding of the sphere, and regularly homotop that to the embedding that composes the standard embedding with a reflection or with the antipodal. Now, it turned out there was a guy named Arnold Shapiro, a well-known topologist at the time, who apparently was sitting in on one of Smale's lectures and figured out how this could be done, how this actually worked out in free space. Unfortunately, he died before actually publishing it. But he told his construction to Bernard Morin, who was a blind French mathematician. This is a very melodramatic story. And there was a state, because Morin, Shapiro's deformation wasn't published until 1980, so much, much later in the Math Intelligencer. But it involved these things called baseball moves, which I heard the word baseball moves at the time, but I had no idea what I referred to. Now, just about the same time, Nicolaas Kuiper, this is what he looked like at that time. So he published, this is a paper about the type immersions, but he gives this example of an immersion of the projective plane, and it's given here by showing slices at various heights. And then he mentions that Heinz suggested to me that an explicit regular homotopy, that's between the sphere and the inside-out sphere, could be obtained via an immersion of P. That's the projective plane. And he says this is indeed the case, and he sketches out how you do it, but he doesn't say, he doesn't give any details. So this is exactly 50 years ago. I had an article in Scientific American where I sort of implemented essentially that suggestion. I thought that I thought this was Arnold Shapiro's idea, because at the time nobody really the history of these ideas was very confusing, and it turned out this was something that came to me from René Thom, but he must have gotten it from Kuiper, although he didn't mention Kuiper in his letter. That's the way it was before. Now, in 1967, a completely different scheme for turning the sphere inside out was devised by a French physicist named Marcel Froissart and Bernard Morin. what I mentioned before. Morin was blind, so he made these plaster models to explain to people what he had in mind. And he gave me this one, so I have this. Took a picture, a couple of pictures of it. Then that model, that deformation got published, but again much later, in 1979, a beautiful article in the French equivalent of Scientific American, which is called Pour la Science. And this is just a little snippet of there's lots and lots and lots of wonderful pictures by this guy, Jean-Pierre Petit, who was a real artist, a wonderful mathematical illustrator. Now we come to 1976, and what happened was that Morin explained his idea to Charlie Pugh, who's sitting in red there, and Pugh made a series of models. We'll see more of them later. That hung in the common room at Berkeley for quite a while. That they were mysteriously stolen. Anyway, there they were. And that's what they look like. And they made Nelson Max made a movie.
Mathematically by getting the sphere inside out.
Okay, so we're going to see part of the way they approach that. Now here's Stephen Smale.
15 years ago, I was working on a general problem one of the simplifications that a sphere could be turned inside out. So naturally enough, I tried myself to turn the sphere inside out. I made many attempts, and I failed in those attempts. But one thing I learned from these attempts was that it seemed to be possible that one might be able to turn the sphere inside out. And that possibility gave me confidence to go ahead and complete the analytic proof required by the general theory.
Thomas, what led you to actually decide to build models? Because it must have taken quite a while and a lot of work.
Well, it did. But the reason I was doing it was because I was trying to understand the geometry that's implied by Steve's theorem. That Steve's theorem is completely abstract and doesn't mention too much geometry in it. At least you can't see the geometry. These models are an attempt to see what's going on. Now, let me give you a tour of the model.
So I've just taken snippets from this video of these are actual. I think they hung Charlie's models in a dark room and illuminated them and photographed them. And here's the guy who made the movie.
After I had each of the models in the computer, I told the computer to move the corresponding vertices, in a smooth way from one model to the next, so as to show the intermediate frames of the movie.
So this is the deformation. At the time, this was really the state of the art of computer animation. There was nothing had been done like this. And as Nelson said, it was done by taking Charlie's models, measuring points on them, feeding them into a computer, and then getting the computer to interpolate between one model and the next one in a continuous way. They always had creepy music. So what you just saw there, what they call the halfway point. The immersion has fourfold symmetry. with the right side out sphere, and then you go through this central level or stage, say, that has fourfold symmetry. Okay, and the way it turns out is that these parts are from the inside of the sphere, and these parts are from the these parts are from the outside of the sphere, these parts are from the inside. And so what you do is you just rotate it by 90 degrees. That interchanges the inside parts and the outside parts, and then you just run the process backwards, and you get the sphere turned inside out. It's really, you'll see more of this, but it's quite a wonderful construction. So the next progress, there's a fellow named John Hughes who's in the computer science department at Brown right now still. He made a completely interactive version, so he had it in the computer, and you could make it, you could turn it, make it go forward, make it go backward in time. You could control all the dimensions. Unfortunately, he did this as a demo for a computer company called Stellar that went out of business. And all that remains is what you're going to see now, this sort of short video clip. But you can see his cursor, right? If you look at it, it looks like a fly, right? He's actually he's manipulating the image on the fly, so to speak.
With the same deformation as the gold.
This is the same one, right? This is also the Morin deformation.
Right.
But if you wanted to study it, it was really great to have it essentially living inside the computer, so you could just turn it around, look at it. That's it. Okay, moving along in time, George Francis published a topological picture book where he has lots and lots of wonderful pictures, but in particular, pictures of the Morin's inversion. You can see here, here's that central stage with the fourfold rotational symmetry. But he remarks in this book that you can do it with center stage with 2, 3, 4, and 5-fold symmetry, whatever number you want. He thought up all these sort of infinite family of inversions. The next, now this is something completely different. Phil Thurston had a completely different approach to the regular homotopy problem, and he had this wonderful movie made. I'm showing just a little piece of it.
It is surprising, but watch this.
Is this it? Is this a sphere turning inside out?
You bet. Think of the sphere as a stack of circles, deformed into a barrel shape, and closed off by caps above and below. Just as we made our curves more pliable by dividing them into guide segments connected by waves, we divide the barrel into guide strips that alternate with wavy strips. The waviness dies out at the top and bottom, so as to match the caps.
This is going to get complicated.
Then for now, let's look at a single guide strip along with the caps. Start by pushing the two caps past each other.
Before, when I pushed the poles through, it made a crease.
Stop before the crease, when the guide has a loop in the middle. Now we turn the two caps in opposite directions, because we want to convert the loop in the middle to twisting at the ends. To finish the eversion, we just need to push the middle of the guide strip back through the center of the sphere. Here is the whole process with all the guides.
The polar caps just move up and down and then rotate into place. Ah, that's why they don't require any springiness.
Exactly.
The next progress in graphics was the Optiverse. So this was a project. This is George Francis again. You'll see him.
eversion turns a mathematical sphere inside out, without ripping or pinching its surface. Our sphere eversion is different from earlier ones. It is computed automatically by minimizing the elastic bending energy. To turn a sphere inside out, we bend it up, increasing energy, until we immerse halfway stage, and then let it relax back down to the round sphere. Let's watch this eversion again without transparency. The outside of the sphere is painted yellow to red, while the inside is blue to purple. The computer uses polyhedral approximations to the smooth surfaces. The triangulation is updated as needed during the eversion. Is join in performing 2, 3, 4, and 5-fold symmetric eversions.
Recently, there's a new entry in the competition from an Australian guy named Iain Aitchison. This one is quite elegant, but a little bit hard to understand. So you have these 4 pieces that fit together properly, and then something's happening. So there's kind of a principle here is that the more elegant the solution is, the harder it is to understand. So what I'd like to do is tell you about the original one that I drew for Scientific American, which was very inelegant, as many of the subsequent commentators reminded me. But it has the property that after an initial deformation, essentially everything is a planar deformation. Everything is like watching circles moving in the plane. And our minds are much better equipped to do that than to understand things that are intrinsically three-dimensional, with things coming in and out and up and down and back and forth. So this is like eversion for dummies. And it's all built on, if you look there, the most significant section, and obviously is that central one. So what I'm going to do is show you how you can turn this thing inside out, but just by moving it in the plane. And the secret is actually that there's these 2 saddle points, a green one, which is above a yellow one. We're going to rotate the green one 180 degrees. So let's start. Here, let's see, we use this, I guess. Oh yeah, let me back up a minute. So how is this connected to the rest of the sphere? If I extend it a little bit above and below, you get these annuli. And then you can extend the annuli to, I call them hemispheres. Right, there'll be kind of a green hemisphere and a yellow hemisphere. Right, because this one over here, actually, although it looks quite green, is secretly yellow, right? If you sort of to undo, if you push this thing out here, it will turn into a yellow hemisphere. So you got a green one, a yellow one on top, and a green one and a yellow one on the bottom. And when you put the whole thing together, you get this thing here, which you can think of as, with not too much trouble, you can think of this as a regularly homotopic to a yellow sphere. Right? You take a sphere, you start pushing two fingers through the sphere, you get this nice simple thing in the lower left-hand corner, and then you enormously distort the right-hand lobe here. So it becomes all of this big stuff up here and the stuff behind. Right? And then what's left over is this yellow knurl here just appears as a kind of a, sort of like a torus stuck onto the outside of the sphere, but in a singular way. Okay, so let's start turning this guy inside out. So here's another copy, just for reference. So the first thing I'm going to do is just move the two saddle points apart, right? So I just slide one up. This is to make the drawing easier because it's very hard to draw intersecting saddle points freehand. And then I'm going to start. I want to rotate the top one, so I'm going to get these. It's like a frog, right? Get these frog's legs here out of the way. So I'm going to move them over to the right. There's one, and there's the other, right? So, see, it has a little loop in it, and it keeps that little loop over there. Okay, now I'm free to turn it, so I just turn it. That's 45, 90, 135, and 180. So essentially, all the work has been done, but I just have to rearrange the bands to get them into a more symmetrical configuration, so you can see what's happening. So let's just start with just moving the bands one by one. So here, I'm taking this band down here. You can see it has two loops in it, right? And I'm pulling it across that undoes those two loops, right? Okay, that takes care of that one. The next one is this one here. Nothing much happens to this one. I just move it over to the side and make the loop a little bit bigger. Okay. The next one is this one. I move it up from below the saddle to over the saddle. When I do that, that introduces a little loop in the corner there. Okay, I've got one more to worry about, I think.
This loop was created.
Well, here it is, right? If I push the yellow part above the saddle, right, it's going to make a little loop over on the right. Here, let me do with the laser. I'm pushing this yellow part up above the saddle. If I do that, it forces a loop here. Right, this has to loop to get the yellow part above the saddle. See that?
Not yet. You don't need to find it there.
Huh? Do it again?
You don't need to stay. Oh, okay. All right. Good.
Okay. I move it up. Okay. Okay. The next one. Okay. Then I'm keeping with the same one. I'm gonna shoot it over so that loop fits inside the loop that's already on the right. So watch this. It's just like something extending out. It just shoots over, shoots back, shoots over. All right. And now I have something that's beginning to look quite symmetrical. In fact, at this stage, I can push the saddles back together. Well, let me do a little adjustment there. That was just essentially for aesthetic reasons. Push the saddles back together. And
so one is rotated now.
Can you go back to push the saddles together again?
Yeah. So everything's staying stationary. The green saddle is moving down, just stretching the bands that are attaching it. Right, if you look at the it has four corners, and each of the corners, you can check them separately if you like. They're each moving down smoothly. Okay, a little more cosmetics. And now if you look at this immersion, you can see that everywhere there are two yellow sides. Whoop, what have I done? Sorry. Two yellow sides facing each other. Right? So this is actually a double cover of a single immersed surface, which is in fact part of the projective plane. In fact, if you look back at Kuiper's paper, and you look at those three central levels, you can see exactly what we're looking at. Right? There's that little arrow is pointing to the saddle point, and then above the saddle point you have something with a smooth boundary, and below the saddle point you have something with a smooth boundary. Whoop. Sorry, I wanted to. Right, this is the thing I want you to compare with Kuiper's picture. So it's really, it has the same. I think it's because I was working from a picture like that initially, but it turns out to have the same orientation and everything. Okay, so now we push those two levels closer together, and now I can do one more deformation where I just push one level right through the other. And this is the only step in the process where there's actually a change in z coordinates. Otherwise, everything was just staying in the same z equals constant plane. But when I go to the next step, right? Actually, I just changed the colors, of course. You can think of it as the yellow one is moving up and the green one is moving down. Okay. And now we just undo everything. We derotate the saddle. This is our original. Here's the green those hemispheres I mentioned. After you, whoa. All right. I'm missing a slide, but it's okay. Okay, so
these are all the pictures inside the magazine article?
No, these are a new set of pictures. But the ones inside the magazine article, unfortunately, were not copied exactly correctly by the Scientific American artist, so there's a problem there. Anyway, you might ask what happens to the rest of the sphere while all this maneuvering is going on in the central stage. So let me look at the upper left hemisphere, which I'm calling the green hemisphere, and it's attached along this circle that I've highlighted in blue. Now let's watch what happens to that circle when I go through the deformation. I'm going to go quite rapidly. But here's the stage where you shift. You interchange the two levels, the two saddles, and then you go back. And what happens is that the circle that was on the right, bordering that upper green hemisphere, has migrated over to the left, where it still borders the green hemisphere. What you can see is that that's a green hemisphere that's been partially poked out. So actually, I think maybe that's how you word it. Anyway, so here's the green hemisphere before. There we go. And so, focus on that green hemisphere. After the deformation, it's moved over to the left, and it's still a green hemisphere. So the hemispheres themselves don't turn inside out; they just interchange. Right, the green one gets swapped with the yellow one, and the same thing happens on the bottom. So that's really that's the main point. And then, of course, you can continue with the reverse the previous homotopies and end up with a green sphere. So actually, that's all that that's all that I prepared for this. Go back and look at details if you want, or replay the octaverse or whatever.
I have a question.
Yes.
During all these years, it's a fascinating math question, but I always want to think, is there practical application? I mean, some invention you could make or something? Have I thought of those ideas? Have you heard of any discussion like that?
No, because the trouble is that surfaces don't pass through themselves. Right. They're So this guy, Jean-Pierre Petit, wrote a like a comic book presenting this eversion. And he invents something called traversine, which is some kind of liquid you can paint on the surface, and then it can pass through the film. But, you know, it has to be magic. You can't do it with ordinary stuff.
If you go one dimension higher,
yes,
then you can, I guess, just turn the sphere inside out. Right? That's the trivial thing. But
you mean the two-sphere in four space?
Yeah. But
well, I guess
this
that
process
doesn't make any sense, right? There's no inside and outside.
That's right. But is there some... if you do this in 4 dimensions, can you do something isometric so that it goes out into the 4-dimensional space, comes back in, and is turned inside out? I mean, I'm not saying you work in 4 space all the time.
You probably could, but it wouldn't be... it'd actually be a homotopy through embedding.
In other words, the in-sphere are n+1. Only for the two-sphere this works. If you get the higher dimensional, we can't do this.
No.
Dora is asking about the two-sphere in higher dimensions.
Oh, but I'm asking different questions.
Right, but I'm still answering his question. Yeah. It's essentially a rotation. It
Would it just be trivial to make them isometry?
Well, it's just like the way if you have this circle, right? And you want to change it into this circle. Okay, you just rotate it, up through, rotate it around like this in free space, and it comes inside out. Right? You can do that with the sphere, but that doesn't count. Right? You're not allowed to go into the 4th dimension.
I press someone on the thing.
It doesn't work for the 3-sphere, or it does work?
You talking about the 3-sphere in R4?
Yeah. In other words, is this beautiful story limited to 2-sphere in R3, or does it work for?
Well, it turns out this thing works because pi 2 of SO3 is 0. Right? There's these things are classified by their tangent maps essentially, which gives you an element of
so if you
a map.
put the one above pi 1 of SO2.
Oh, I see.
Right. Pi 1 of SO2 is not 0. Right? And then I forget what pi 3 of SO4 is. Okay, so that means that there's you don't have a similar theorem.
G plus D.
Yeah.
So going back to the history, so I'm confused about what Smale had actually proved. So he didn't provide a construction himself, I guess, given us all of...
Right. He proved that if you take the map from the immersions of the 2-sphere into R3 and you send it to tangent bundle monomorphisms, that this map is a weak homotopy equivalence. In particular, it pairs up connected components with connected components. So if two immersions have their tangent maps are homotopic, then the immersions themselves have to be regularly homotopic. And this thing essentially boils down to this fact here, that there's only one connected component.
So what's the answer then for converting a torus? You can't do it then?
No, the torus is much easier.
It's easy.
Right, but you...
I visualize that easily.
Well, I mean, given all the work we've done, there's sort of a simple way where you take your torus and you extrude a little sphere, right? Then you turn that sphere inside out, right? By the process we've just seen, right? Then you make that sphere very big.
You just pull the torus along with it and illuminate what's attached.
Yeah, right. It just rides along, right? I mean, you make it very, very small, right?
So far, it's not easy.
Right, and then you just reach in and pull the torus out, right? And it's inside out. But there's another following analogous to this one. You can go from the torus to the double cover of the Klein bottle. The Klein bottle is a much simpler animal than the projected plane. Right? It has no triple points, for example. It's a much simpler surface. So it's a much easier thing to visualize.
The immersion of the Klein bottle is simpler than the immersion.
Yeah. Yes. Well, I think the convoluted is kind of simple-minded compared to projective space. And then you get
the point is that once you have an immersion of a non-oriented surface in R3, then that automatically, just by taking a small neighborhood of it, you can move.
That's right. You can interchange the two leads, but then you still have to know that
those two leads.
That double cover is regularly homotopic to the standard front of the torus. Because the torus has several different immersions. There's 4 homotopy concepts.
Yes.
So, in the video, there's like a mention of, you have this sort of 4-fold symmetry in the middle.
Yes.
And there are other ones where there's like 5-fold symmetry and
Right.
6-fold. Are those homotopy equivalents?
I don't think so. No, because the animal you get in the middle, right? If you do the one with 3-fold symmetry. No, maybe it's the one with 6-fold symmetry. There's this point that the immersion of the projective space. There's a very nice immersion of the projective space called void surface, which looks something like. How does it go? I mean, it has 3-fold symmetry. You have what's this stuff drawing it? I'm not going to draw the whole thing, right? But it has. Then this goes like this, and this goes like this. It looks. It has an immersion. This is void surface. Void surface has naturally a 3-fold symmetry, which is not exploited in the Kuiper eversion at all. But if you were to deform, of course, the double cover of a void surface has to be regularly homotopic to the regular sphere. And that double cover would have essentially 6-fold. It had like 6 handles. And apparently what Poisson noticed, he read my article, and he said, what Phillips does with 6, I can do with 4. And that's how they got this 4-fold central state.
So when you're trying to analyze Mark's question, do you come up against the fact that pi 3 of SO3 is Z? And you're looking at homotopies of these. That would seem as a.
What's the fundamental group of this space?
I don't know. There's a so you're looking at a loop in the space of mass from S2 to SO3, right? You're looking at something like this, right? And the question is, but that's someone here should know the answer to this question. Right? What happened to Dennis? At least.
You knew you were going to ask.
I have a feeling it's probably something like pi 3 of SO3,
yes,
which is Z. Right? So there probably are many different paths.
Right. So you already have an energy's worth of, by looking at these things with different symmetry, I guess.
That's right. That's right.
That actually occupies the different positions.
Presumably that would do it. Yeah. Yeah. Thanks for asking. That's a good question.
Any other question? I had a question about a slide, but maybe I have to ask Tony about it later.
A slide?
Yeah, there's a couple I didn't understand. There's one in particular. Was there one like Omnivision or something? 1996?
The Optiverse?
Optiverse.
Well, we have a couple minutes. If people will bear with us, we can just run back. You can see it's almost like a movie.
Yeah, we should get someone to interpolate.
Yeah. Wait, what? This one here?
I thought it's made the next.
I thought it was the Australian.
This one?
No. We'll have to go through them later on.
That's it. I mean, there's only...
There's one of them mentioned algebra.
Yeah, that's controversial.
That's this one here, the mentions algebra. Right. In fact, this
was that was the dedication.
That was the dedication, right. The math they use actually relies on the work of Robert Bryant. I meant to mention that, but I forgot. He studied this Wilmore energy, which is what they minimize to create this deformation. Yeah, it's cool. It's a little bit creepy, I think. But anyway, right.
Especially the music they chose. I know two of those guys. I guess it's not so much.
What I thought was creepy was that it says 1996, but then it gives his death is 1997, and how did they know that?
Oh. The movie was made.
That was what I thought was kind of morbid about it.
It's okay, you
And
do
if you
the
can
calculations on top.
Together it was like weird.
It's not like gruesome, but anyway. I'm not sure it's twist more. I don't know what happened to the soundtrack. Anyway, luckily it lasted.
The music's much better now.
Oh, actually, that's what you were asking about. Think of that. I don't have any way of playing it fast, but at the end he shows four of the family of eversions.
I don't know how they got that. How did they? What?
I don't know. They're a little bit. I mean, George doesn't really say. Yeah. Yes.
I know that Cherita in Toulouse also found this paper, and he mentioned that he's also studying this steel eversion, and he also has a movie.
He has a very nice movie, but it's of the torus.
Oh, it's of the torus.
It's of the torus, and it's a very, very simple. I mean, it's totally simple way of turning a torus inside out, but it doesn't work for a sphere.
He has given talks showing his aversion to the sphere, but
he has.
Perhaps he has a few classical and his next public. Yes.
I see. Do you have any idea which model he follows, or? I should write him.
So for surfaces of higher genus, when you're trying to calculate how many different classes there are, how many components there are to the immersions, how do you do that? What does the calculation come down to?
The fact is, whenever you have an whenever you have a non-trivial annulus in your surface, right? There's two different ways of immersing it. I mean, there's a standard way, and then there's the way with one complete twist. If you have two twists, if you have two complete twists, that's rarely homotopic to the standard one. So for each, if you have a surface, it has a lot of
two generators. I mean, two elements of pi.
Whenever you have a surface, right? So whenever you have each independent annulus gives you a dimension of different immersions. Like for the torus, there's 4. And I didn't calculate for the surfaces of higher genus, but you could do it. Yeah, it's probably just 2 to the genus, or 2 to the genus minus genus plus 1.
I see. So if you're just looking at homotopy classes of maps to SO3, they'll just be classified because it's K by 1 will just be classified what happens on the fundamental group.
Yeah, that's
to do with a Boolean group.
Yeah, so it's just
but you can actually see it.
Okay, that's thank you.
Okay, thank you very much.